Good morning, everyone. Myself, Chanpreet Kaur, working as an assistant professor in the Department of Mathematics, Janki Devi Memorial College, University of Delhi. So, today I will present a lecture on linear transformations. So, to define a linear transformation, I will assume that my domain and codomain they both are vector spaces over a field F. So, a transformation is nothing but a mapping, and a linear transformation is a mapping that satisfies a particular condition. So, let's first define a transformation. So I am assuming that U and we have two vector spaces U and V. A transformation T from U to V is a mapping that assigns to each vector small u in the domain vector space capital U a unique vector small v in the codomain vector space capital V. Now, when do we say that a transformation is a linear transformation? So suppose we have a transformation T from U to V. So this transformation is said to be a linear transformation if it satisfies T applied to u plus v is same as tu plus tv, and t applies to a scalar times vector u is c times tu. So this is the graphical representation of this definition one can see. So u and v are vectors. So this is the resultant vector u plus v. Whereas under the action of t, we have tu and tv in v. So t of u plus v should be same as tu plus tv. And similarly, u times, if we have c times u, the vector, scalar multiple of the vector u. So under the action of t, this t applied to cu should be equal to c times t. So let's look at some examples of a linear transformations. So suppose t is a transformation from r square to r square. Here my vector space is r square. U and v, they both are same. So t applied to xy, a two tuple xy is x minus y and 3x. So here basically we have to see two operations. Vector space has two operations, addition and scalar multiplication. So we pick two vectors in the domain vector space R square. So T applied to x1 y1 plus x2 y2. So first we just add x1 y1 and x2 y2 by applying the vector addition defined in R square. So according to the transformation T transforms the two tuple xy as x minus y and 3x. So we have just applied the definition, and by simple calculations we can see that it satisfies T of u plus v is tu plus tv. Now with scalar multiplication, for the scalar multiplication, let's look at this. So let C be any scalar. So T applied to C times x1 y1 is T applied to. So this is just simple scalar multiplication of C with any vector in R square. So under the action of T, this is the action of that I have applied. So it turns out to be that T applied to C times x1 y1 is C times T applied to x1 y1. Hence we can say that T is a linear transformation. So when my vector space, domain and codomain vector space, they happen to be same. So T from U to U, it is called a linear operator. Another example. So if I take a transformation T from R square to R cube to R square, such as T applied to X, Y, Z is XY comma Z. So let's pick any two vectors in R cube and we look at the action of some of these two vectors under T. So T applied to the first vector added to the second vector. So by simple vector addition in R cube, we get component wise addition of these two vectors. And now if we see the action of T under this, so we get T applied to x1 y1 z1 plus x2 y2 z2 as x1 plus x2 multiplied by y1 plus y2, comma, z1 plus z2. But it is not same as the action of t applied to x1, y1, z1 plus t applied to x2, y2, z2. So here the first property is not satisfied, so there is no need to check the second property. So we can say that it is not a linear map. Now for the third example, so I have a case of polynomials, real polynomials up to degree n. So let Pn denotes the vector space of real polynomials of degree less than equal to n. And we have a transformation T from P2 to P1 as T applied to ax square plus bx plus c equals a plus bx plus c. So P2 is polynomials, real polynomials up to degree 2, and P1 denotes the real polynomials up to degree 1. So what is the action of t? T applying to ax square plus bx plus c is a plus bx plus c. So basically we are collecting the coefficients of the quadratic and linear term. We are adding them and we are multiplying it with x plus constant term is kept as it is. So under the addition, under the action of under the vector addition, so we find t applied to x square plus bx plus c plus the other polynomial px square plus qx plus r. So we are adding them as we add any two real polynomials. So simple polynomial addition is applied here. So under the action of t, let's look at the action of t on this polynomial. So simply we are adding the coefficients of quadratic and linear term here, multiplying it with x plus constant term c plus r is kept as it is. By rearranging the terms, we will simply obtain that t applied to this polynomial plus this polynomial is same as t applied to the first polynomial added to t applied to the second polynomial. And similarly for the scalar multiplication, t applied to a scalar times polynomial is equal to scalar times t applied to the same polynomial. So it was a simple exercise to see that this is a linear transformation. Now the next transformation is the operator of differentiation. So we have an operator d from Pn to Pn defined as, so d takes a polynomial f to f dash simply. So for example, if I have applied d on this polynomial, so we are simply differentiating this polynomial. So for any f and g in Pn again, Pn denotes the real polynomials up to degree n and c be a scalar. So if I take d as a linear operator, so the action of d is of differentiation. So differentiation operator is a linear operator. So it is simple to see that d applied to f plus g is df plus dg and d applied to scalar times f is scalar times df. So next is matrix transformation. So every matrix defines a transformation. So how do we go about it? Let's see. So suppose I have a matrix 2 cross 3 matrix with me 1 3 minus 2 0 4 and 1. Let's assume a column vector x y z in R cube. So matrix defines linear transformation like this. We take T applied to X as AX. So this T is clearly a mapping from R cube to R square. So this X was a vector in R cube arranged in a column form. So Tx equals to Ax is a linear transformation. So if I simply consider Tx is nothing but Ax. So simply multiply this matrix, this 2 cross 3 matrix with this 3 cross 1 matrix, and we get this transformation. So this matrix actually represents a transformations where Tx is defined like this. And it is a simple exercise to see that it is a linear transformation. So if A is an m cross n matrix and X is an element in Rn, interpreted as a column matrix, then if I take the transformation defined as Tx equals to Ax, then it will definitely be a linear transformation. It is also called a matrix transformation. It is very trivial to see that Tx equals to Ax represents a linear transformation. So we can simply check these two properties, and hence we can say that it is a linear transformation. So this exercise, this is a simple example. So I'm just leaving it for the time being. Now let's come to the composition of two linear transformations. So suppose I have different transformations with me. So suppose we have u, v, and w as three vector spaces. We have t1 as a mapping from u to v. So t1 is a transformation from u to v. T2 is a transformation from v to w. These are two linear transformations. And u, v, and w, they are all vector spaces over a field F. So how do we connect two transformations? How do we combine two transformations? So basically we uh, combine two transformations using the operation of composition. So this is a pictorial representation of composition of transformation. So T1 is a transformation from U to V, T2 is a transformation from V to W. So to compose them, we need to have that the range of U should be contained in the domain of the range of T1 should be contained in the domain of T2. Here we have these vectors. So the codomain vector space for T1 is same as the domain vector space for T2. So composition is a uh, well-defined operation here. So here we are defining the composition. So T1 composed with T2 will be T2 O T1. So we call it T. So T will be a mapping from U to V. So just like we define composition for functions, in the similar fashion we are defining composition for linear transformations as well. So how do the composition operator acts here? So T u let u be a vector in the domain vector space, that is capital U. So T of u will be, so T here I have defined as T2 OT1, T2 composed with T1, T2 applied to. So next example, example number 6, we have to find composite of this these two mappings T2 OT1, and the actions are given, and we need to determine the image of 2 comma minus 3. So just like simple composition, we compose these two mappings. This is the resultant mapping, and the image of 2 minus 3 is simply we put the values here. So image of 2 minus 3 turns out to be 12 and 1. Next is a theorem which says the composite of two linear mappings, linear transformations is again a linear transformation. It's a simple proof. So we will simply use the properties that T1 and T2 both are linear transformations. So T2 OT1 composed with each other apply to U plus V. So these are normal definitions of the compositions applied with the definition of a linear mapping. We will get this result. So it's a simple exercise to see that the composition of two linear transformations is again a linear transformation. And a similar way, composition of two matrix transformations is again a matrix transformation. So T2 composed with T1x will be T2 applied to T1x. T2 T1x is replaced by A1x, where A1 is the matrix representation for T2 for T1, pardon me, and A2 is the matrix representation for T2. So it is a simple exercise to see that the matrix transformations again result, the composition of two matrix transformations again result in a matrix transformation. So this is a simple example, and this is an exercise, so you can verify yourself whether determinant mapping is a linear transformation or not. Now we come to the next topic, a matrix transformation. So how do we obtain a matrix representation from a linear transformation? So suppose Rn, so here Rn is a vector space, and we consider the standard ordered basis E1, E2, so on, En. where E1 represents the column vector 1, 0, 0, 0. So here for E1 we have 1 at the first place and rest of the elements are 0. For E2 we have similarly for E2 we have 1 at the second place and rest of the elements are 0 like that. And En is all other components are 0 and the nth place we have 1. Let U be a column vector A1, A2, An. So suppose U has this representation. So we can always express U as A1, E1 plus A2, E2, so on, An, En. So how do we get the matrix out of it? So we see the action of T on U. So T, as we have represented U as A1, E1, A2, E2, so on, An, En. So U is replaced by this representation. So since T is a linear transformation, we apply the properties of linear transformation and we get that it can be written as A1TE1 plus A2ET2, TE2 and so on, ANTEN. And we simply collect the actions of T on ETI. So we rewrite this as the row vector TE1, TE2, so on, TEN multiplied by the column vector A1, A2, so on, AN. And this is how the matrix representation is given. So basically the first column of this matrix A will be defined by the action of uh, T on the first basic element, that is action of T on E2. The second column of this matrix A will be evaluated by the second column will be evaluated by the action of T on E2 and so on. Similarly, the last column of this matrix A will be evaluated by the action of the transformation T on the nth basic vector. So this A is called the standard matrix of T. So let's have an example to evaluate the standard matrix for a linear transformation. So suppose Txy is defined as Txy equals 2x plus y, 3y. And so first of all, we'll evaluate the action of T on the standard basis elements E1 and E2. So clearly this is the vector space, underlying vector space here is R square. So TE1 is T applied to 1, 0. So under the action of T, it turns out to be 2 into 1 plus 0 and 3 into 0, which is 2, 0. Similarly, the action of T on the second basic element, that is E2, is T applied to 0, 1, which is 1 and 3. So the standard matrix will be given by, so first column will be determined by the action of T on the first basic element, that is action of T on E1. So hence I just arrange these two, this column vector 2, 0 here. And the action of T on the second basic element E2 is given by 1 and 3, and we arrange it like this. So if I rewrite it like in the matrix transformation form, so Tx equals Ax will be the matrix transformation form. Now we define the kernel and range for a linear transformation. So for that, uh, so let T from U to V be a linear transformation. So let 0 subscript U, it is denoting the 0 element for the vector space U, and 0V denotes the 0 element of the vector space V. Then T applied to 0 of the vector space U is mapped to the T is the 0 vector of V. So basically, a linear transformation always maps a 0 vector to a 0 vector. The proof is very simple. So I'm just skipping this. So basically, we want to define here kernel of a linear transformation. So suppose I have a linear transformation T from U to V. So how do we define kernel of a mapping? So here we have vector U, vector V, and T is a mapping from U to V. So kernel basically it is a set In fact, it is a subspace, but right now let's just consider it as a collection of elements from U only. So basically, kernel of T is collection of those elements from the vector space U which are mapped to the zero of the vector space V under the action of T. So set of vectors in U that are mapped into zero vector of V is called the kernel of the mapping T of the linear transformation T. And kernel of the linear transformation is denoted by KER. Within brackets, we mention the linear transformation, that is T. So ker T. And what is the range of a linear transformation? Just like range of any function, range of a linear transformation is nothing but a subset. It is a subset of the codomain vector space V. So range, the set of vectors in V that are the images of vectors in U. So they comprise of range of the linear transformation V. So the kernel of a transformation and range of a transformation, they form a subspace for any vector space. So we are assuming that so to study these linear transformations, we are assuming that basic vector spaces and their properties and the definition of a subspace. So subspace, let me just quickly recall what is a subspace. A subspace is so basically for a vector space V, a non-empty subset W is said to be a subspace if W itself is a vector space with respect to the operations of V. So a subspace is basically a subset of a vector space which in itself is a vector space with respect to the same operations of the vector space V. So, so we claim here that kernel of T and range of T, they both form subspace of U and V respectively. So let's see. So A part. So we'll prove that the kernel of the linear transformation is a subspace of U and range of the linear transformation is a subspace of V. In B part, we'll prove this. So first of all, we'll show that these two sets, they are non-empty subsets. So definitely a linear transformation maps a zero vector to a zero vector. So T will definitely map 0 of U to 0 of V. So kernel T is definitely non-empty. So to show it to be a subspace, so you must have done a criteria for proving a subspace during studying vector spaces, that to prove a subset to be a subspace, we need to prove basically two properties. The first, of course, is the non-empty thing we have to prove, and after that, we need to prove two properties, that we need to prove that that set is closed under vector addition and scalar multiplication. So in order to show that kernel of T is a subspace, I'll pick two elements here, U1 and U2, and I'll try to prove that U1 plus U2 also belongs to the same set kernel T. So since U1 belongs to kernel T, so definitely T applied to U1 will be mapped to 0. This is the property of, of a vector to belong to kernel T. This is the condition that U1 must satisfy. Similarly, since U2 also belongs to kernel T, then T of U2 is also 0. And we consider T of U1 plus U2. So it turns out to be that since T is a linear transformation, so T applied to U1 plus U2 is TU1 plus TU2, which is 0 plus 0, and it is resulting in 0. So T applied to U1 plus U2 is giving me 0. It means U1 plus U2 belongs to kernel T. And similarly for the scalar multiplication, so we consider T applied to C times U1. Since T is a linear transformation, this can be rewritten as C times TU1, and TU1 is 0 because U1 is a member of kernel T. So this gives me that CU1 belongs to kernel T. So kernel T is satisfying the properties of being a subspace, therefore it is a subspace. So it is closed under, we can say that kernel T is closed under vector addition and kernel T is closed under scalar multiplication. Similarly, for the range, definitely 0 of V can be represented as T applied to 0 of U. So this element has a pre-image in U. So it is a member of the range space. It is non-empty. So range space of T is definitely non-empty. Now we assume two elements V1 and V2 in the range space. So there must exist two pre-images W1 and W2 in U such that T applied to W1 should give me V1 and T applied to W2 should give me V2. So now we consider T applied to W1 plus W2. Since T is a linear transformation, it turns out to be TW1 plus TW2, which is V1 plus V2 in return. And here we get that V1 plus V2 has a pre-image, namely W1 plus W2 in U. Since U is a vector space and W1 and W2 are members of U, so their sum is also a member of U only. Hence, V1 plus V2 has a pre-image, namely W1 plus W2. Hence, V1 plus V2 belongs to range of T. For scalar multiplication, let C be any scalar, and we consider T applied to C times W1. So, by the property of linear transformation, it turns out to be C applied C multiplied by TW1. Whereas V1 was a member of range, therefore V1 can be written as TW1. So here simply we get that CV1 has a pre-image, namely CW1 in U. Therefore CV1 belongs to range of T. So here we have an example where we will evaluate kernel and range of a linear operator. So we consider this kernel and range. So T is given to be a mapping such that T applied to X, Y, Z is X, Y, and 0. So kernel T is T applied to, so kernel T basically consists of those elements which are mapped to 0. So T X, Y, Z equals X, Y, 0. This is the definition of T. So basically I'm collecting all those elements of the domain vector space which under the action of T are mapped to 0. So under the action of T, this element should be mapped to 0 and the condition for that is that X and Y should be 0. So kernel T turns out to be 0, 0 and Z where Z belongs to R. Similarly, range space consists of elements of the form X, Y and 0. So this mapping that we have just discussed is also called projection mapping. So basically we are projecting X, Y, Z, this vector onto XY plane. It is also called an object so this is also an example of a projection operator. Now we will determine, let's do one more example. So here we have a matrix and we need to determine the kernel and range of this matrix. So for that, we are converting into a matrix transformation basically. So Tx equals to Ax is the matrix transformation. So we simply evaluate Ax from here. So Tx equals to Ax is the matrix transformation for this given matrix. So basically, I'm interested in all those elements such that those elements under the action of T should be mapped to 0. So Tx equals to 0. So we are trying to solve this equation, this system. Tx equals to 0. Tx equals to 0 turns out to be Ax is equal to 0. It gives rise to a system of linear equations. And we are simply solving it. And it turns out to be scalar times minus 510. So just the way you solve a system of homogeneous equations, to solve it like that and you will be able to find that the solution, so the system will have infinitely many solutions and it turns out to be this. So kernel of T is generated by the vector minus 5, 1, 1. And when we come to the range space, so basically range space is spanned by, so you will apply matrix transformations and you must have done this in your first year linear algebra, that how to find the range spaces. So it turns out to be that the range space is spanned by these two column vectors. So range turns out to be ST and S plus T. So this was about the basics of linear transformations. So here we have studied the meaning of linear transformations. We did some examples where the transformation was linear, where the transformation was not linear. Then we saw how to combine two transformations to generate a third transformation using composition operator. We learned about matrix transformations and we defined kernel and range of the linear transformation. So that's it for today. Thank you so much.